All right, so in this video, I'm just gonna really quickly go over a classic ring opening type of question. Um, this is a classic ring opening question dealing. So it's a dehydration reaction that has a little bit of a carbocation shift in the intermediate step. And again, this is just a really classic ring opening mechanism. Instructors, professors they love to ask this one on free response exams. So especially if you're at a university where they have free response exams with organic chemistry. This is going to be a classic ring opening type of question. So let's just go ahead and get started. The first thing I like to do is, so I rewrite H2SO4 as HOSO3H. The reason I do that, it just makes it a little bit easier to see. Also, organic chemists are kind of lazy. It's a little time consuming to draw out the Lewis structure of sulfuric acid each time. So it just makes it a little bit easier to see that HO bond in sulfuric acid. So I don't like to draw out the entire Lewis structure of sulfuric acid, just in the interest of time. But so the first thing that's going to happen in every acid-base mechanism is protonation. So you're going to protonate that alcohol. You're going to protonate this alcohol right here. So this secondary alcohol, there you have it again. So one of the electron pairs from oxygen is going to grab that hydrogen. It's going to get protonated. So you're going to protonate that hydroxyl group. And again, those electrons are going to jump to oxygen, and you're going to form this intermediate right here. So you're going to form your hydronium intermediate right there, plus obviously hydrogen sulfate, like so. All right, now you've formed a good leaving group, so the electrons from that bond are going to jump onto oxygen, and water is going to leave essentially. So that's the next step, is to form your carbocation. So that's what happens next, is you form your leaving group, and the leaving group leaves, and you have formed the secondary you formed a secondary carbocation there. So that's your intermediate. So that's your secondary carbocation. All right, so here is the tricky part. So here is the classic ring opening. So we formed a secondary carbocation, correct? We formed a secondary carbocation. However, we can form a tertiary carbocation here. And actually, there's two reasons for the formation of that tertiary carbocation, and I'll explain what those are in a second. But yes, so this ring is going to open up. This ring is going to open up, and so you're going to take the electrons from that bond right there, from between this carbon-carbon bond here. So these two electrons, and those two electrons that bond there is going to open up and attach itself right there on that carbon right there. So that's the next step that happens here. So that's what's going to happen, and the product of that is simply going to be something like this. So something like that. And there you go. And in order for us to get a better picture of what's happening here, I'm going to call this just arbitrarily carbon A. That's carbon A, and this is carbon B. Okay, so where does carbon A end up? And so the place where carbon A ends up is going to be right there. So then where is carbon B? So carbon A is attached to carbon B. So carbon B is right there. And sometimes I like to do that. It helps me just keep track of where my carbons are at and what I'm doing in the mechanism. And then, just as something additional you can do is label carbon C. So if we label this as carbon C, where would carbon C end up in our intermediate step here? and carbon C ends up right there. So that is carbon C. Okay, so what have we done? We've gone from a secondary carbocation, right? So we've gone from a secondary carbocation to what kind of carbocation over here in our intermediate step. So we formed a secondary carbocation as well. So why did the ring open up? So why did the ring open up? What is the whole point of the ring opening here? Why does that ring open up like that and form a six-membered ring? Why can't we just work with the secondary carbocation over here and call it a day? So the reason for that is because you can. This is a little misleading here. Truthfully, it's more than just a secondary carbocation. And the reason for that is because it moved adjacent to this oxygen, which is even better than a secondary carbocation, because now you're resonance stabilized here. And so that's why the ring opens up, because you've formed a secondary carbocation. However, that positive charge is next to the oxygen, which is way, way better than any stabilization provided by an alkyl group. So it doesn't get as good as that. It doesn't matter how many carbons you have, it doesn't matter how many electron donating carbons you have on that secondary carbocation, it doesn't get as good as an oxygen. So being next to an oxygen is really, really favorable. And so just to illustrate the point here, on this next slide, I am going to draw out one of the resonance structures. So you have resonance stabilization like so, putting the positive charge on oxygen. And so this resonance stabilization is really, really favorable, because now you can move that positive charge around. And so in nature, nature prefers that lower stability, so that lower energy, which is, higher stability, not lower stability. It's higher stability, lower in energy. So that's why you form that secondary carbocation there, and that's why that ring opens up. So now what happens is, we have, let's go ahead and start over here. So we have this hydrogen here, right there, and remember we formed hydrogen sulfate, and that's our conjugate base, and so our conjugate base is therefore going to go after that hydrogen, and the electrons from this carbon-hydrogen bond are going to collapse right there. Again, let me draw in our carbocation here. Let's not forget about that. And so what happens then is you form that carbon-carbon double bond that dehydration product right here that we're looking for. And so yes, there you go. That's how you form this product here. So right there, that's how you form that product from this starting material right here. So that's how you get that product. That's why that ring opens up. The ring opens up because the formation of the carbocation adjacent to an oxygen atom is really, really, really favorable, again, due to higher stability and lower energy. So resonance stabilization here is a major, major driving force of this reaction. It's really, really crucial that you all keep in mind. If you can draw an intermediate in which your carbocation is resonance stabilized, then the reaction mechanism will always follow something that is resonance stabilized over something that is simply providing electron donating effects from, let's say, like a carbon-hydrogen moiety, so like a methyl group or an ethyl group. So you could always follow the resonance stabilized intermediate, and that's how you form your final product right here. So thank you all for watching. Go ahead and subscribe to my channel, please. I'm going to be going over more problems, just classic problems. This is a classic test question in an organic chemistry free response exam. Professors love these ring opening problems, and honestly, it doesn't get any worse than this. If you can understand this one, you pretty much understand them all. So go ahead. Thank you so much for watching. Stay tuned for the next video. Thank you.